take a break.
Alright,
So,
and the bag's right here.
that's what I was showing you here.
I
So
don't know
once
where you
again,
wanna-
these RSs stand for the SNPs.
Yeah, the other batteries.
And basically what we can do is, we could ideally do it for every single SNP, so all of these. But what we normally do is, I'll pick a few in each of the blocks. And that's usually what we do is actually cover our bases. We're going to go over what the overall, how many we need to have at the very end of this lecture. So keep that in mind, back of our head. So we can do it that way, using the color coding with the bases. We could also do it this way, where we basically want to have a flash of light that wants to occur. Where what we're going to have is same idea, oligonucleotide, our DNA sequence. We're adding bases onto the oligonucleotide. However, it must be the right base to phosphate base pair with whatever the SNP is. And this is what we do is, what happens when we add a base? What do we always produce? Pyrophosphate, right? We have a trinucleotide, you get rid of triphosphate, you get rid of two of those phosphates, pyrophosphate. Normally the pyrophosphate then does what? Degrades away, and then we're done, right? However, in this case, we've added some other players to it. So what we do is, we still have the pyrophosphate being created, but basically you're going to have these two other proteins. I think the biggest one you guys know is luciferase. So it sounds weird. Basically you have pyrophosphate, and as soon as you make a pyrophosphate, those enzymes take that pyrophosphate and use that energy, and they produce light. So they produce a little burst of light. And that's what goes on here. So what we do is, we have our chip with all of our DNA and the oligonucleotide, and we add, do we add all the bases or one base at a time? If we add all the bases, what would happen in every single block? You get a white light. And okay, great. Something got added, we have no idea what. So we add the bases one at a time. So we have this here, I now add A. And everywhere on that whole chip, on some places I will get a burst of light. Why? Because I've added a nucleotide, I pop out the pyrophosphate, the sulfurase and the luciferase took pyrophosphate and created energy, created a light from that. And then that light shows up on there. So if I added the A, what is the SNP there? The T. So therefore, once again, I know the T is the SNP there. So I do it for, I add A all throughout the chip, wait, add T, wait, add C, wait, add G, and then wait. And therefore now, I can then say, for every SNP, oh, the light source came here because luciferase took that pyrophosphate and used that for energy to create that light source. And that's all this is right here. Another way to do this is we do PCR. So we have three different ways. We've got the DNA microarray using the fluorescently dyed bases. We use a DNA microarray using luciferase, making a light source, using one base at a time. And three, we can do just general PCR. In this case, how do we do it? Well, I want to look at the SNP in particular, right? So let's go back to exam 1. Everyone remember PCR? What's the general idea? We have our DNA, what else do we need to have to add to it? The primers, the polymerase, and then that's some other things, right? And it grows and grows and grows. But if the primers don't bind to the DNA, do I get amplification? Do I get PCR? No, the primers must bind to the DNA. So in this case, what we do is we have a certain low-level amount of DNA, or the person's DNA. I then add the primers. In this case, the primers are going to directly bind to the SNP. So the SNP is going to be used as part of what's binding to the primers. So I have different primers then for the different SNPs. So let's say the example here is a G. So what binds to G is C. So the primer I add, if I have a T on the primer, will it bind to that area of the DNA right there with the G? No. I must have a C in the primer to bind to the G. If I don't have that there, I don't get amplification. So in this case, it's not, remember VNTRs, the primers are outside the VNTR on either side. In the case of this, I don't care about this, I'm not sequencing anything. I just want to see, do I get PCR amplification or do I not? That's the only goal of this. So if I add the primer that has a C on it, the C does bind to the G, and therefore the primer binds to the DNA, and then DNA polymerase can make more of the DNA. If I get amplification, that tells me I know the SNP was G. If they have a T instead of a G, if they've got a T right here, and I add the same primer with a C, is that C going to bind right there at that T? Remember, it's not just one, it's usually like 10 or so base pairs. But within there, I must have nice Wadsworth base pairing. If my C, it can't bind to the T, therefore I don't get amplification, that then tells me, well, C, it's not a G that's up there. Because if it was a G that was up there, I would get amplification because the primer I added had a C in it. So in this case, we are designing primers that directly bind to the SNP. I'm not sequencing anything. All I'm looking at is what SNP is it. How to identify the SNP, which SNP it is based on if the primers will bind, and if they do bind, I get amplification. It does that for like 5 seconds, right? So, we're looking at GWAS studies for type 2 diabetes. Once again, looking at SNPs, remember, SNP stands for single nucleotide polymorphism. If you don't remember, a polymorphism just means differences between people in the population. That's why alleles are polymorphic, big A, little a. SNPs are polymorphic, I have a G, you have a T, you have a C, whatever it is, right? So here, we're going to go into stats a little bit. Don't worry, it's not really important, but remember, so once again, the RS number, that just means a SNP. What's the p-value? Do you want a high or a low p-value for significance? Low. You want the lowest p-value you can get. So the smaller p-value means it's a more significant value. In this case, what that top blue diamond is saying is that there is a statistical difference between the disease population that have this SNP and the normal population that don't have this SNP. Does that make sense? It's saying this SNP, let's say it's an A, people that have the A SNP right here, they're within that block, that A is traveling with whatever the disease allele is going to be for that disease, whereas normal population could have a T, or maybe even a C, or some other thing there, and therefore in those blocks, they're not traveling with the bad allele. That's all it's saying. So the lower the p-value, the more significant the results are. In this case, we're looking at differences between disease state and healthy or normal person, normal population. Why is it going up? Is that because on here it's the p-log value or whatever, negative p-log value, or it's like inverse. That's why the higher up it is, it's a smaller p-value. So all these ones down here, there's not, there's still some variation, but this p-value is not nearly big enough to call it significant. Which means that looking at this allele or this SNP, I didn't see any variation in those blocks. Why? Because those blocks don't contain a gene responsible for causing the disease. Only these blocks do, and those blocks are all going to be traveling within this unique haplotype block. Or those unique SNPs, sorry. Same idea here. CDK, cyclin-dependent kinases, we've seen that before. It's going to be on the cancer lecture, all the different proteins and stuff. But obviously here, once again, it's a negative log value of P. That's why the higher it is, the smaller the p-value is. Blah, blah, blah. Statistical significance. Once again, we're always, in this case for disease, when we're looking at diseases, I think, maybe not, don't quote me on it, but I think for here we're talking about, we're doing studies, we're always comparing disease population, normal population. Those are our two groups. And if something is statistically significant, it's going to be different between the population, normal population, and the disease population. Which means if they're linked, they're within the haplotype block. They always travel together. They're in linkage disequilibrium. Same slide again. So, here are the examples he uses. And there could be other ones on the exam, but these are some of the big ones you should hopefully feel pretty comfortable with. So we have a disease state. And we see people with the disease, of that group, 69% are going to have a G-SNP at one, let's say haplotype block 245. Just make up one of the blocks. So this is the location in the genome. At that block, people with this unique haplotype block that have a G here, 69% of people that have the disease have the G-SNP there. 31% of the disease state could have any of these other SNPs of them. So why isn't it 100%? Why isn't it 100% that have G have the disease? Why is it only 69%? Because it's a quantitative trait. It's not saying this is the only gene that's going to wreak havoc and be responsible for it. It's a quantitative trait. However, and once again, just reading this is not enough to tell me if that SNP is part of that block. Why not? What's the only info given to me in this first bullet point? Do I have any info on the normal population? No. So I have no idea. What if the normal population also has 69% of the G SNP? Then there's nothing special about it. That's why these go together. You can't, that's why the line is down here, all right? Once again, whenever we're talking about, especially on GWAS studies, you have to always ask yourself, what's the disease population and what's it compared to the normal population? So we have to have both, bullet points there. So once again, it says everyone has this disease. They have the disease. Of that group, 70% of them have the G SNP at whatever this haplotype block is. The other ones have the other ones. The other disease patients have different SNPs there. That's okay, number one. It's a quantitative trait. It's not just this SNP means that to occur. Or, even if it is just one gene, could this still be possible? If I have a haplotype block, can recombination ever occur within there? Yes. It's just less likely. Now, it wouldn't be 70 and 30. It'd be a little different percentages, but you can still get some variation even within that. But that first point doesn't tell me shit unless I know the second point. The second point is telling me what the normal population frequencies are. Because down here it says, well, they had 69% have G, and they have the disease state, versus the normal healthy population at large has 25% of each. That's where my difference arises. If the second bullet point said 69% of the population has the G SNP, then that tells me that SNP isn't important. There's nothing different about that versus the normal population versus the disease state. So always be comfortable and always be aware of disease state versus the normal state. And Blake can definitely trick you with that on the exam. Once again, on the flip side, if there is no difference in the frequencies, once again, if both groups have a 90%, they have that T-SNP, both the disease population and the normal healthy population at large, no difference, therefore there is no statistical significance between the two groups, and therefore that block probably doesn't hold our gene that we're looking at right now. Once again, we're still looking at this. This is not talking about the allele. We're focusing on the SNPs that travel with that allele in that haplotype block. Slide for the 10th time. Slide from the last exam, or last lecture, right? Once again, you got the chiasma. What does the chiasma stand for? That's where we get that crossing over. That's where we're going to have that point. Is there only one chiasma occurring during homologs? No. You're going to have multiple chiasmas, multiple points of crossing over that will be occurring. And is it always just one sister of one and one sister of the other? No. These two are going to overlap and the other ones overlap. Remember, it's like spaghetti and the stuff's all mixed up. Recombination is going to occur between both this sister chromatid from mom, this sister chromatid from dad. Those recombine, but the outside ones do as well. The whole thing is recombining, right? Keep in mind, these two are sister chromatids, and those two are sister chromatids. Are red and gray the same? No. They're similar. They have the same genes. Where do they have this different? SNPs, VNTRs, and alleles.
It's the difference of paternal and maternal.
Exactly. Paternal is one of them, maternal is the other. Same slide again for the 10th time. Yep, okay. Same thing again. All right, cool. Let's take a 3-minute break, and then we'll get through the rest of this one, and then we'll work into again. Sorry, I know kind of...